Swayam Prabha. Digital India. Educated India.
So this particular semantic analysis is definitely complicated, very complicated. Of most of the languages it's a real complicated stuff, remember that. And I will just highlight some of the things that how basically semantic analysis is done, but it's a real complicated module and phase of the compiler. Okay. Other things are much simpler, because if there is a, in fact, to ensure that, okay, I don't know whether you have heard about this. So all this basically, whenever you are writing a real time systems and all, the compilers are supposed to pass certain validation tests. Okay, so there are validated compilers actually, and they need to pass that they are generating the right code. Okay, and obviously that so their test suite is extensive and very complicated in fact. Okay, so they thoroughly tested that, okay, this particular compiler will never generate something which can actually cause this machine to fail, or the program to fail because of the wrong translation. Obviously compiler is also a program, and there are programmers who are writing it. So there is a bug, then there is a big problem. Okay, normal program, what will happen is that you may miss certain address or certain maybe it's a 1 rupee instead of that 2 rupee will go, it's also okay sometimes. But if there is a some bug in this kind of mission critical applications, then it is a obviously it can be disastrous. Okay, you can either miss a target, or you may have a, in fact, air crash also sometime, right. So all these things, it is this semantic analysis phase is a very important. It has to bring, and then obviously the code generation phase is also important. Optimizers should not do something which is if it feels that something need not be optimized, it should not do optimization. Unoptimized code is okay till the time it basically is a correct. Okay, and you can prove that it is correct, you can prove that it is correct, but the thing is that writing a buggy optimizer is not a solution. So this is a very important thing, that all these compilers and all, it becomes a very challenging for all this kind of in this kind of scenario. Okay, okay, now this is an exercise that you need to do now. You have seen this particular this two, three things about the parse tree, about the abstract syntax tree, etc. So this is a small exercise you need to do. Draw a parse tree and abstract syntax tree for this particular expression b star b minus 4 star a star c. The grammar is given here. Grammar is given here. You have to write. You can use computer. You need not use a computer. You can use notebook. Whatever way you want, you do it. So two people can do it together, that's okay. Two of you can, or you can do it alone also. If you want to do it alone, you can do it alone, or this you have done the syntax analysis multiple times, right. So this should be easy, in fact, should not take more than 10 minutes. Simple exercise this is. One person can do it on his own, or two of you can do together, but it's a very simple, let me tell you that. Parse tree, remember that you have to draw a parse tree and AST. So 10 minutes break, I will 10 minutes for break for me, not for you, sorry, you do the exercise. Okay. So the way the grammar is written is automatically it is taking care of that associatively, correct. Good. So coming back to just recap, this is a basically full maybe a complete view of, okay, what happens, but obviously this is a very simplistic view of the compiler phases and the way as we have been discussing, but you are through with this, right. You have understood this particular part, correct. So we have a scanner, then it tokenizes, then there here I have used that ID1, ID2, etc., which may get added into a symbol table at the lexical analysis phase itself. parser which is driving that overall syntax directed translation when we are talking about it. Then we are constructing this abstract syntax tree which gets annotated, then we generate a intermediate code which we optimize, and we generate the code like this one here. You are familiar with the x86 and this one, maybe some other kind of other of these machines basically. So move ID3 to R2, move multiply 60.0 with R2, that is basically what is the assembly language that is shown here, correct? Any question? No question, right? We can move forward. Okay. Now let us look at the basically now let us get into the more deeper that I just showed the brief about this particular machine instruction set and all this thing, correct? I just showed a brief about this instruction set for a particular expression, correct? Now overall what happens is that you have written a code and which gets compiled, and you create a obviously either Java bytecode or maybe a machine code for a particular target architecture, right? So there are multiple options that you have, the target machine. So you need to understand whenever you are doing the optimization, rather than more than the optimization, the code generation and optimizations around the target architecture, then you need to understand for what target I am generating this particular code. Okay. So the backend is generally kept as a independent of the front end. Okay. Front end that we talked about, the lexical analysis, syntax analysis, semantic analysis up to certain point, that is basically language dependent. But when it comes to the backend, they are more they are kept language independent many times, and it is a good idea to keep them language independent. That is a commercial compilers will always try to make it more and more independence from. So there are obviously for that you will require a certain standard definition of intermediate representation which can be used by any compiler front end to generate that. So you might have heard about the Java bytecode and this JVMs being used by multiple languages nowadays. It is not only the Java. Have you heard of that? No? You heard of it? Okay. So there is a Scala and all this thing, they also use this JVM. They are also called as the JVM languages, okay, because they also generate it in the bytecode and it gets basically executed by Java virtual machine. So you need to keep that particular front end part and the back end part separate, and that is a general idea. Now what kind of basically machine target architecture is, depending on that you will generate the code. So if it is a stack based machine or it is a obviously the normal register machine like our target architecture, you need to generate it accordingly. This particular generation, as we mentioned some time back about how the variables will be allocated a storage, and all this thing need to be also considered. Now those things we have not talked about it, we just shown you the flow with a complete system view. I just showed you without any specifying that okay how this I will be allocated a space and all this thing. Okay, we will see that later as we move ahead. In fact, there are multiple intermediate languages and multiple because it depends on the kind of basically complexity or the kind of basically independence they want to keep it. Here what I am showing you is a simple thing that okay, if I am generating a code for Java virtual machine, okay, and the bytecode I am generating, the bytecode actually is a more, it's a in fact our machine code of the actual CPU actual hardware machine is much more basically simpler compared to, and these are more at an abstract level. Okay. So what happens in that case, that for example some of the optimizations you need not do also. Sometimes the optimizations you need not do when you are generating the code for the Java virtual machine. Okay, because that actually the instruction set is much richer there. So there are intermediate languages also. This particular intermediate you can consider them as the intermediate languages itself. Actually, the Java bytecode itself can be considered as the intermediate language sometime. Okay, so this particular kind of Java bytecode and all, they are much richer compared to our hardware architecture based machines. Okay, and the code generation for them becomes much simpler for the Java bytecode and all compared to what you if you have to generate for the maybe i386 or some other MIPS machine, etc. So code generation phases are diluted in this particular kind of interpreters and the languages and the compilers basically for them. Okay. So here if you, let's try to understand this. Have you I have put a slide here. Have you understood that what is written here? On the left hand side there is a icons 2 that is shown here, right? So what does this mean? I actually did Java virtual machine specification. If you read, you will find a description about that. The instructions starting with I are for integer. So you have icons 2, so that gets loaded, and where it gets loaded we do not know that. We will see that part where it gets loaded, how the it executes, we will see that. So 2 is what basically is a 2 as a number that gets loaded. It is stored in 1, it is an integer which is stored as a 1, so it is stored in variable I, okay. And then after that you are loading it again, and then pushing that 1000 to the 1000 is pushed there, short integer 1000 is pushed, and you are comparing it, and if comparison is greater than or equal to, then you are returning it. Very simple, right? Very simple translation here. Are you getting it? Very simple, right? So try to understand whenever I am showing, I thought that you should read that actually whatever I am showing you here, and ask a question if you have not understood, because these are very simple things actually. They are not, we are not getting into the any question. It is storing into the I, correct? It is storing into I, again it is loading that 1, underscore 1 is a particular index of that particular variable, okay. Then and you are loading it again, and then you are pushing 1000 and comparing that two values on the stack, operand stack. Now we will see the structure of this Java virtual machine and the frame, Java frame basically, we will see that later, but here I am just showing you this particular part here. I store 1, actually the way the local variables are stored in case of Java virtual machine frame is different from the other thing. So you are storing it in local variables array, okay, that I store 1. You are loading from there onto the operand stack, okay. We will see that part how it happens actually, but just note it down at this point. Remember that I will, whenever I show that frame of Java, then you will realize that how basically why this is. So forget, I mean those of you who are familiar with Python and all, the Python also has a virtual machine actually, you can see that part. Many times actually if you will find that this particular okay, I think I will skip this part and I will talk about that later. Let's come back to that later actually, because that will be. So what is happening is that we need to, whenever we are generating this code, you have seen this I store 1, I load 1 and all these things. So maybe let's try to understand how this particular processor works in fact, okay. It is basically hardware actually. It's what is happening is that you are seeing this assembly code here, but actually if you are generating for x86, you will generate a machine code, correct. It will be some 0011, 000 something like that, correct. Agreed or no? So what's happening is that basically your hardware in fact is decoding the instruction, and then after that it is driving the certain functionality. Maybe it is a ALU, arithmetic and logical unit, it will drive that, okay. So that's the way it happens. The same thing happens in the virtual machine and the interpreted languages. So virtual machine actually is acting as that processor itself, right. So Java bytecode that is generated actually is for that virtual machine, Java virtual machine, and that's basically interpreting that, and that's a similar kind of approach is used there also. So what happens, this is just to give you idea that okay, when we are generating code, we need to understand that architecture, underlying architecture actually. So you need to understand, whenever if you are generating Java bytecode, you need to understand how this Java bytecode actually Java virtual machine work. So there is a Java virtual machine specification that exists, okay. You need to understand that, and then you need to generate the code. Code generation is a really code generator and a person who is writing the code generator need to understand the underlying architecture quite well. He has to understand, for example, earlier days there used to be specific thing that okay, if I am multiplying by 2, I can generate a shift left shift 1 bit, okay, that's kind of thing. So he has to understand this particular machine code underlying architecture, plus you need to understand okay, how I can generate a better code, okay. Okay, so so remember this part, and also you need to understand architecture means what kind of registers exist, what kind of basically how this particular overall I can generate a basically I can utilize the resources of the hardware. I need to understand that. So whenever, so we talked about that first part, front end analysis, and then the front end analysis is target independent actually. Okay, we are doing a lot of target independent thing. When we are moving to the optimization and actually code generation, we need to be more of it. You need to understand the target architecture, you need to understand the overall basically the approach that we need to take. Now this is a, so this is a basically a x86 and a 64-bit execution environment of Intel, and there what we have is some general purpose registers where some of the registers like EAX and all this thing I can use it as a general purpose for and you mentioned that AX and BX you some time back, that the 16-bit they used to call it AX BX, now it's a EAX and EBX etc. But some of the registers are very important, and that's where we are going to really these two registers we need to really understand quite well. And obviously there is another register called as the EIP, which is your program counter. Okay, your program counter which is actually moving from the one instruction to the another instruction, correct? Now what is this particular ESP and EBP is what we need to understand now. Till now we have seen the generation of a code for an expression, very simple, correct? It's a very simple generation, move and load and I store and all this thing. What happens if I am calling a particular function which is supposed to do certain calculations and return back the value? How I should handle that, how I should handle the recursion, how I should handle the exceptions. So I need to basically, there are certain registers, certain basically mechanisms exist, okay, which allows you to do, which allows you to handle this particular calling sequences. How many of you are familiar with this? No, none of you? Okay. Stack pointer you are familiar. So I think there are some of them which are you can see that here same, correct, but the 64-bit has some of the other things that I have, I think right side I have mentioned here. There are 8 64-bit register for MMX and all this thing. So there are mathematical calculations, some registers exist for specifically 64-bit one, and there is a 128-bit floating and all this thing also exists. It's a RAX, correct. So I should have said that 32-bit and 64-bit both actually, right, thanks for pointing it. So I have, yes you are right, it's a, but EAX is also, you can call EAX also in the case of whenever 64-bit you are using it, okay. Okay. So some part actually this Intel actually when it is extended it is obviously that AX to EAX and all these things. You are, how many of you are familiar with Intel assembly language? You mentioned most of you are familiar, right? Okay, so you may find it similar. Now the thing is that how to effectively use this particular registers, how to where this particular usage of ESP and EBP, how this ESP and EBP is used. Okay, stack pointer and the base pointer, that's what we are going to see actually, and that's where the we will move to the in fact complete code generation actually, because right now we are talking about this expression, we are using a limited set of instructions, right. So I will skip that part. So before we move into that part, let's try to understand that your whenever your program is executing, whenever your program executes basically, you have a multiple data storages actually, multiple things that are you need to refer. You are referring to code. For example, when you are saying that execute that function, you are actually addressing and you are changing the point instruction pointer to point to the different place in that particular code, correct. So you are referring to code. So there is a address spaces, what you can say, there are different address spaces when your program is executing. You are referring to constant, you are referring to constant basically, correct, and that constant is in different address space. Generally it is not mixed with the normal data space because it is not going to change. I can put it in a much different place. You have a, obviously there is a some initialized data and there is a uninitialized data, there is a runtime data, there is a and there is a obviously a heap and all this thing that exists. which is basically something that you allocate with new, and maybe the compiler themselves may be generating sometimes that I need a heap storage area. So you have learnt about the heap and the reference counting and all, right. So there are different address spaces, and the address basically you can say different parts of that particular program that are divided into the different parts basically, where you need to refer them in a different way. For example, instruction pointer will actually change whenever I go through this particular instruction space or the code space. That EIP need not actually be used to refer to constants. I need to refer to the constants, I need to refer them through some particular base point, and I will say that okay, my string is actually sitting at a position 4 from in this particular constant space. I need not actually mix that with my how I am referring to instructions, how I am referring to procedures. Are you getting it? Correct? How I am referring to the stack variable, that has nothing to do with how my basically constants are referred. How I am referring to local variables, stack variables is local variables, parameters should not be mixed with the way I am referring to statics. Everything should be kept independent, because stack is a dynamic kind of thing. It gets allocated when I enter a procedure. Local variables gets created when you enter a procedure, correct? You don't have static variables exists. They are initialized or uninitialized. They are initialized, all of them in Java kind of thing, where they are initialized with 0 whatever. So there is a difference actually the way this particular overall address space is divided. That's the first thing that you need to remember whenever you are generating the so what okay. So I think I have made a slight order. I have to change it basically slightly. Sorry for that. I will go back again. Okay, so my slide actually okay. So coming so what kind of basically the instruction sets exists in your target is what we need to understand apart from this address space allocation. Now we are going to talk about this ESP EBP again. Okay, we'll come back to that. So there are different kinds of instruction. There is a control transfer instruction, arithmetic and logical instruction, data movement instruction. In case of Java bytecode, there are also instruction to throw exceptions. There are instructions for monitoring based concurrency and all these things. So there are multiple instructions that exist. Okay, so I will just sorry for that. I have to skip some of the slide. I will go back to them again. I want to change the order here. So now let's consider this particular two programs. So one is written in Java and another written in C. Okay, right? So one written in Java. So if this particular program, okay, this particular program Java, a very simple program where I have just written a certain functions here. Okay, within a class employee, and there is a another C function, C basically code, which you can compile it using a GCC. Now I want you to do, first of all, what you need to do is that try these two examples and try this particular commands. Okay, try these two commands. Just any of you, if you do not have a Java, you have Java and C both, right, on your machine. So you try both of them, generate this, and then after that what you need to do, after you just execute these commands, just enter these programs, execute this particular commands, and then we will talk about it. Enter this program, okay, execute these commands, and then we will. Now let's even if you have written one program, that's fine. Let's look at that now. We have to. So what some of you must have compiled this particular C program, and some of you might have created a bytecode from this particular generated basically a file or compiled Java file. Okay, the simple program, if you look at this particular simple program that you must have, I have just modified, I have taken some small variation of that okay, you can compare it with whatever the .s generated for your program, but I have taken a slight variation of that particular program, okay, the one that I gave you. The variation is that I am calling here a print message function to print it, okay, because I want to move forward. You have but we will cover both the things. Whatever the assembly language that you are seeing after in the hello.s that you have written, there is a slight variation, but yes, we want to really learn that, okay, what is that basically variation is. If you look at here, this particular program now here, it's calling a print underscore message, right, and that print underscore message, it is calling it is passing a parameter hello string, right. Hello string is passed as a parameter, and that print underscore message is supposed to print ultimately, correct. If you look at this particular code generated for this print underscore message, okay, print underscore message, there is a you can see that, okay, these two this particular two registers that I mentioned that are immediately used here. EBP is the first one that is used, so it is pushing the EBP, pushing the PBP. Where it is pushing? It is pushing on the stack, right, it is pushing on the stack, and it is storing that particular EBP, correct. And then after that, it is saying now I am setting that EBP to ESP, that means I am moving EBP to the I am adding that maybe 4, or sorry, reducing 4 from EBP, or you are moving that ESP to EBP. That is what you are doing. Are you getting it, what I am saying? You are basically now pushing the EBP, which is called as the base pointer. I am just going to give you that particular how basically it gets referred. Now the thing is that if you look at this particular below, you will find that here we are specifying here that, okay, this you want to, in fact, ESP stack pointer is what I am going to use it, and that stack pointer I am going to use it, I am going to allocate the space on the basically stack for the local variable, or to push the parameter, that is what it is doing. So, and then it is calling that particular inbuilt underscore main. The C program, generally what happens is that there is a library underscore main that you need to call it before you actually start working on it. So what it is doing, it is calling that underscore main, and then after that, actually if you look at we are interested more at the after that underscore main, where it is moving the hello string, address of hello string, it is pushing it on the stack, and then it is calling that print message. So how the stack is used, stack pointers and the base pointers, you can look at that. Now stack actually is a dynamic variable, the parameters is getting pushed, and then this particular parameter will be referred here as 8% EBP, okay, 8% EBP, that is basically offset from that particular base pointer is what my first parameter is. Offset, some offset from that base pointer is my first parameter, okay. So this calling sequence, how basically the code gets generated for this calling sequence is just, I want to show it here. We will see that more how this gets generated on, but just try to understand that we talked about a simple expressions, code generation of a simple expressions, okay. But whenever it comes to now the procedure calls, okay, the referring the variables, maybe a local variable or parameters, then we need to use an additional either a storage or the base pointers, so that I can refer to that particular different storages in a different way, and I appropriately insert the basically instructions I specify that, okay, this particular thing is referring to I, this particular thing is referring to j, or this particular thing is referring to n, which is a parameter. In this case 8% EBP is a n. So how this storage allocation is done? When it is done, this particular association of the actual storage that this particular variable will assume, it is done after this semantic analysis, okay. This I just want to repeat that here, it is done after the semantic analysis, and then what you get actually, what you basically do actually when during the code generation, you actually use that offset that has been specified, or storage that is allocated for that variable, and then generate the code, okay, then generate the code. So I just wanted to highlight this particular storage part, and we will get into the deeper on this front again. So is this clear that what's happening in this code? Simple? Any question? You can look at that your Java P code also. I will get into that. Okay, let's take only 10 minutes break and come back. Okay.